Every time you swipe a debit card, buy a house, or log into a secure server, you are relying on a middleman. Traditional digital records are held by a central authority, like a bank, a government agency, or a centralized master server, which acts as the absolute source of truth. But placing all that data in one central location creates a severe vulnerability. If that single server is breached, hacked, or manipulated by a bad actor, the entire database can be altered, hidden, or completely erased. This leaves us with a difficult structural problem. How do you securely store sensitive data and verify transactions without having to place blind trust in a single central middleman? The solution to that problem is the blockchain. As the definition here states, a blockchain is a distributed digital ledger. Instead of one computer holding the master record, the ledger is copied and shared across an entire network. While cryptocurrency is the most famous application of this technology, a breakthrough is the architecture itself, a system designed to guarantee data security and absolute trust without requiring a central authority. Curious, this diagram breaks down the core unit of the network, the block. Every block is a container that holds 4 specific pieces of information. It stores the transaction data, a timestamp of the entry, a unique identifier called a hash, and the hash of the block that came immediately before it. That third component, the hash, acts as a unique digital fingerprint. When data is entered into the block, a mathematical algorithm converts it into a fixed-length sequence of letters and numbers. This fingerprint is sensitive to the data inside the block. If you alter even a single character or digit in the transaction data, the resulting hash completely randomizes into an entirely new sequence. This algorithm operates strictly in one direction. You can generate a hash from the data, but it is mathematically impossible to take the hash and reverse engineer it to figure out what the original data was, because any microscopic change to the data immediately generates a brand new hash. Secret tampering becomes impossible at the block level. The block itself will instantly announce that it has been altered. This diagram illustrates how these individual blocks form a continuous chain. Every new block is required to securely store the exact hash of the block that preceded it. The fingerprint of block 1 is embedded directly inside the data structure of block 2. If a hacker attempts to alter a transaction in block 1, the data changes, which immediately scrambles block 1's hash. Because block 1's hash has changed, it no longer matches the historical record stored inside block 2. The mathematical link breaks, instantly invalidating block 2 and every single block that follows it in the chain. This cascading mathematical defense system creates immutability. Immutability means that once a record is written into the chain, the system is designed so it cannot be altered or deleted. To successfully fake a past record, a hacker would have to simultaneously calculate and rewrite the hashes for every subsequent block in the chain before the network noticed. This astronomical computational requirement renders the historical data practically permanent. This map shows the macro architecture of the system. Instead of sitting on one central server, a perfect synchronized copy of the entire chain is distributed across thousands of independent computers, known as nodes. The network is entirely egalitarian. There is no master node, and no single computer has administrative control to force changes. Every node must independently verify the truth of the ledger, but without a central authority to approve transactions, the network needs a way to agree on which new transactions are valid. They do this using a consensus mechanism, a set of rules that all computers follow to reach an agreement. This split screen shows the 2 most common rule sets. On the left is proof of work, which requires computers to solve complex math puzzles to validate a block. On the right is proof of stake, a more energy-efficient model where users lock up their own digital tokens as collateral to earn the right to process blocks. Under either rule set, a new transaction follows a rapid 6-step lifecycle. A user requests a transaction. It is broadcast to the network. The nodes validate the data. The transaction is grouped into a new block. That block is added to the chain. And finally, the ledger updates across all nodes. By combining rigid cryptography with distributed consensus, the network creates a self-policing ecosystem. It naturally identifies and rejects fraudulent entries without relying on a human intermediary. Now that we have a fully transparent, immutable network that secures data permanently, we can build more complex tools on top of it, starting with smart contracts. This logic gate diagram illustrates how a smart contract works. These are self-executing digital programs stored directly on the blockchain. They use strict if-then parameters, triggering an action, like releasing a payment, only when pre-programmed conditions are verified by the network. Because the code enforces the agreement automatically, these contracts eliminate the need for expensive, time-consuming human intermediaries, like escrow agents or financial clearinghouses. This architecture scales to diverse real-world systems. It enables precise supply chain tracking, secure digital identities, tamper-proof voting mechanisms, and protected healthcare records. The technology still faces friction points before it reaches mass adoption. Processing thousands of decentralized transactions requires complex code, meaning many networks struggle with slow scalability, and proof-of-work systems demand extraordinary amounts of energy to operate. Yet the core achievement remains intact. Blockchain provides a secure mathematical solution to the ancient human problem of how to guarantee truth and establish trust on a global scale.